Hello and welcome back. Today I want to look at a feature introduced in LTspice 17.1, which, in a nutshell, helps you create results similar to an AC simulation but using a transient one, the Frequency Response Analyzer, or FRA block. While it is presented as a tool mainly needed to help in switch mode power supply loop analysis, it can do quite more than that. So if you're curious, then keep watching. So let's start with the two basic types of simulation that you will find yourself using most often. On the one hand, you have the transient type of simulation, a time domain simulation where you analyze the behavior of a circuit over a defined period of time. In this example, we have the 555 timer IC's internal structure, and we apply a square wave on the input, which is then modulated using a higher frequency generated by the IC. So with this type of analysis, we can easily see how a circuit evolves over time and how it passes through various nonlinear states. In this case, we have a very clear switching behavior added in the output of this circuit. Now, another example of a transient simulation is the 100-watt amplifier circuit, where the purpose is to apply an input sine wave of different amplitudes and to calculate the total harmonic distortion appearing on the output signal. So this time we have a linear type of circuit responding to a single frequency sine wave. But we still need the transient to observe how the circuit behaves as the input signal becomes larger and larger. While we should have a fixed gain and similar response, this is not always the case. And that is exactly what you investigate using the transient simulation. In contrast, the AC type of simulation is a small signal analysis where the simulator first checks the operating point and then applies a small signal on the input. So an infinitesimally small amplitude, but of a fixed frequency, and then analyzes the response of the circuit at that specific frequency only. It's great for analyzing things like linear circuits. For example, this filter simulation. You can observe how signals of different frequency will be affected by the circuit. So the input is constant, but the output is variable. And you can observe how the response is affected by varying one of the components. So if you need to observe how a circuit works over a period of time, you need a transient simulation. But if you want to see how it responds to a range of different frequencies, then you use the AC simulation. But there's a major problem with the AC one. Well, two actually. First, it's a small signal analysis. You will never see things like distortion or saturation. And second, it analyzes the behavior of the circuit around the operating point. This is great for linear circuits like a Class A amplifier or a passive filter, but it's not so good for switching circuits, like switch mode power supplies or switching amplifiers. So this is where the FRA block comes into play. So in a nutshell, the FRA block allows the creation of gain phase diagrams, but rather than using AC simulations, you're using a transient one. The main types of examples provided in the library that highlight this function are related to switch mode power supplies. So there are quite a few examples that you can play around with to get a better understanding of this block. And well, the results that you'll be getting is something like this: the gain and the phase of the supply's feedback loop. Now, long time ago, I covered this possibility in LTspice when I showed how this can be done the hard way. So there were a lot of measurement statements that were needed to extract this information, but the end result was more or less the same. You get the phase and gain information about the circuit from a transient simulation. But this method is way too complicated. Using the FRA block like this is a far more convenient way of doing the same thing, and you have far more control over what you're doing. Now, before moving forward, let's look at what the FRA block actually does and how it can be used. How do the results it produces in the transient simulation correspond to what you would be getting in an AC simulation? So, in the components menu, you have both the FRA block as well as the FRA probe. Let's start with the block first. In this example, I just used a resistor in parallel with a capacitor, and the FRA block is configured in one of the two options that it has. This time the impedance versus frequency is selected, and to get this thing working, we need to define a stimulus. So we need a start and end frequency and a number of points, as well as a stimulus amplitude. Here I just put 1 ampere, so for the impedance analyzer the stimulus is a current source, and this value is constant throughout the frequency interval. And while everything else I just left open. Now to run an FRA simulation, in the simulation setup we need to select the transient frequency response type of analysis, and if we hit OK, we can now run the simulation, and we get the impedance as calculated over the requested frequency range. So it starts off at around 1 kilo ohm, and then it slowly drops off as the capacitor's contribution becomes more and more significant. Now we can compare the results to an AC simulation of the same circuit. So I made more or less the same circuit with a current source of amplitude 1. And if we run this second circuit and we check the voltage present on the current source, so the impedance will be the voltage divided by the current, which is 1. And if we also change the scale from decibel to logarithmic, so after doing a bit of resizing, we can see that the impedance on the right side, as well as the one on the left side, is more or less the same thing. Our next example focuses on the gain versus frequency type of response. So this is mainly applied to closed loop circuits, like this linear power supply. I added the FRA block in the feedback loop and configured it in more or less the same way as before. It's just that the gain versus frequency type of measurement was set. In this case, the simulator will be looking at the voltage ratios and phase differences between the two terminals of the FRA block. So if we run the circuit, we get this nice graph showing the gain of the feedback loop, starting at around 80 something decibels, and then going down to about -20 over the measured frequency range. And while the graph also points out some important parameters, like the frequency where the gain becomes unity, which is this F0 frequency at 1.027 MHz, as well as the phase at this point, so our phase margin, about 63 degrees. Now, just to check the result, we can also compare this to the same simulation but done as an AC type of simulation. And well, if we add the ratio of the two signals present in the feedback loop, we get more or less the same result again. Last example to highlight involves the FRA probe block. So the idea with this is that you need the FRA block as a stimulus. This will be injecting a test signal into the circuit, but the results will not be extracted from the block's terminals, but rather from wherever the FRA probe is connected to. So this has a set of differential input and output probes, which can be connected anywhere into a circuit, and the response is calculated based on the ratio of these two. So in this case, we have a basic LC filter, the FRA block is injecting a signal on the input, and then the probe will determine the ratio of the input to output. But just a small observation, the input and the FRA probe are on the same net, just for simplicity. They don't really need to be connected like this. Anyway, if we do simulate, we get the response of the LC filter by plotting the probe 1 trace. And our result can easily be confirmed if we also do the same simulation as an AC simulation. So we are getting the same results again. Now, this is nice and all. The AC and the transient frequency response simulations are giving us the same results. This is not something too helpful for anything other than confirming how the FRA block works. So let's now look at some examples where the transient simulation will tell us things that the AC simulation could not. So first, I have a basic amplifier where the signal source is a 100 ohm resistor in series with the FRA block, and the output is again a 100 ohm load. And while our FRA probe measures the ratio of input to output, so the gain. Now, we could have done this in an AC simulation, but what makes this special is that the FRA block has the amplitude set as a parameter, so this amp, which I am stepping using the dot step statement. So the point of the simulation is not just to observe the gain of the circuit, but also the effect that the variable signal amplitude has on this gain. So if we run the circuit, we can also probe various nets. So let's say we look in this place. And the first important thing to note is that the circuit is analyzed by injecting a variable frequency signal, but the circuit does not instantly stabilize to the new stimulus. So if we just zoom in a bit, we can see that after every change in step, there is a period of accommodation. So the transition, is not instantaneous. This exact period will be circuit dependent, so this period needs to be analyzed on a case-by-case basis. And to make sure we are getting the correct results, in the FRA block definition, it is important to also consider the minimum analysis time at each frequency, as well as the stimulus settling time at each frequency. So how much time is ignored, as well as the time that is being considered. And based on your exact circuit, you might also want to take advantage of the time at the start of the analysis. So if the circuit needs a bit of time to just get up and get started, this will also be needed. Anyway, to get our results, we need to select this other window and right-click, add traces, and select our probe one. So here we can see for our specific circuit how the gain is decreasing as the incoming signal becomes larger and larger. So for example, this pink one is our fifth step where the amplitude was 1. The second circuit to look at is a Class D type of amplifier. So this is the most basic version just to highlight the operation. And here we have an incoming signal, again from our FRA block, which is then compared to a triangle waveform by our comparator. And then this drives a simple push-pull stage, which in turn is filtered and then applied to an output load. Now the simulation is using the FRA probe again, and it's set up to determine the gain of the amplifier, so the ratio of the input and the output over the given frequency range, which was set in the FRA block. So this is something that cannot be determined if we ignore the switching bit. So the gain is impacted by the output filter, the input coupling capacitor, but also this switching stage. So if we run the simulation just to see what happens, and we wait quite a bit for it to finish, and we plot the results the same way as we did before, so we add in the probe 1 trace, we can see our low frequency corner as well as the high frequency one, but we can also see that in between, things aren't really flat. There is a bump, which is not supposed to be there. So this amplifier does need a bit of work before it could be even considered for audio applications. This just will not do. Now, the final example I want to look at is one of the default examples the program comes with, and it's built to highlight the loop response of the LT7170. So the FRA probe is placed in the feedback loop. And well, if we run the simulation, the results are plotted instantly as the simulation is finished. But the thing I wanted to point out is that for a measurement such as this one, you usually vary two parameters. On the one hand, you wish to inject a set of frequencies, so to span a specific range. In this case, the FRA block is going from 32 kHz up to 500 kHz. But the other thing you play around with is the injected signal amplitude. So while for all of our previous examples we used a fixed amplitude over the entire frequency interval, for this sort of loop measurement, you commonly start with a larger signal amplitude and then gradually decrease it. That is why in the stimulus block, we have two different frequency points defined with two different amplitudes. So when needed, a variable amplitude stimulus can also be used. In the end, the FRA block is an invaluable simulation tool when your objective is to analyze either switching circuits or when you need to observe how a signal's amplitude affects functionality. While the simulation itself may take a while to be set up and run, it's usually way faster than doing the same simulation piece by piece, one at a time, and then somehow combining the results. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.